Good evening, students. I am Mr. Arockia, Assistant Professor, Department of Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore. We are going to see theorem for MSc Mathematics students, finite extension. First, we see a lemma. The polynomial f of x belongs to capital F of x has a multiple root if and only if f of x and f dash of x have a non-trivial common factor. Proof. Before proving the lemma, we consider a remark. If f of x and g of x in f of x have a non-trivial common factor in k of x, where k is an extension of f, then they have a non-trivial common factor in f of x for where the relatively prime elements in f of x. Then we would be able to find two polynomials a of x and b of x in capital F of x such that our a of x into f of x plus b of x into g of x equal to 1. Since this relation also holds for those elements in k of x, they would have to be relatively prime. Now coming to the proof, from the remark we made above, we assume without loss of generality that the roots of f of x lie in f. That is, if f of x has a multiple root alpha, then f of x must be written as x minus alpha the whole power m into q of x, where m is strictly greater than 1. However, it is easily computed x minus alpha the whole power m dash equal to m into x power x minus alpha power m minus 1 by lemma 551 f dash of x equal to x minus alpha the whole power m into q dash of x plus m into x minus alpha the whole power m minus 1 into q of x equal to x minus alpha into r of x. Since m greater than 1, this says that f of x and f dash of x have common factor x minus alpha. On the other hand, f of x has no multiple roots, then f of x must have all the distinct roots, such as f of x is equal to x minus alpha 1, x minus alpha 2 and so on into x minus alpha n, where each alphas are distinct. Then f dash of x is equal to summation I is equal to 1 to n x minus alpha 1 and so on x minus alpha I and so on x minus alpha n, where the up arrow symbol denotes that the term is omitted. Now we claim that no root of f of x is a root of f dash of x. That is, f dash of alpha I is equal to pi j not equal to I, alpha I minus alpha j not equal to 0, since all these roots are distinct, which is a contradiction. However, f of x and f dash of x are a non-trivial common factor. Thus, they have a common root, namely any root of this common factor. Therefore, the result is f of x and f dash of x have no non-trivial common factor. So, the lemma is proved. We see a definition. The extension k of f is a simple extension of f if k equal to f of alpha for some alpha in k. Then we see a theorem. If f is of characteristic 0 and if a comma b are algebraic over f, then there exists an element c belongs to f of ab such that f of AB equal to f of C. Proof. We consider two polynomials f of x and g of x of degree m and n, and the both be irreducible polynomials over f, satisfied by a and b respectively. Let k be an extension of f in which both f of x and g of x split completely. Since the characteristic roots of f is 0, all the roots of f of x are distinct as of in g of x. Let the roots of f of x be a, which is equal to a1, and the other roots are a2 to am, and g of x be b, which is equal to b1, and the other roots are b2 to bn. If j not equal to 1, then bj not equal to b1, which is equal to b. Hence, we get the equation ai lambda bj equal to a1 lambda b1, which is equal to a plus lambda b, which means lambda equal to a minus a divided by b minus bj. Since f is of characteristic 0, it has an infinite number of elements. So we can find an element gamma belongs to f such that ai plus gamma bj not equal to a plus gamma b for all I, and for all j not equal to 1. We consider C equal to some a plus gamma b such that we have to prove that f of C equal to f of ab. Namely, we have to prove that f of C is subset of f of ab and f of ab is subset of f of C. First, we show that f of ab is subset of f of C. For that, both a and b are in f of C, from which we can easily say f of ab is subset of f of C. On the other hand, b satisfies the polynomial g of x over f, hence satisfies g of x, considered as a polynomial over k, which is equal to f of C. Moreover, we take another polynomial h of x, which is equal to f of C minus gamma of x. Then h of x belongs to k of x, and h of b equal to f of C minus gamma b, which is equal to f of a equal to 0, since a equal to C minus gamma b. From the result that C equal to a plus gamma b. Thus, in some extension of k, h of x and g of x have x minus b as a common factor. We assert that x minus b is in fact their greatest common divisor. For bj not equal to b is another root of g of x. Therefore, substituting bj in h of x, h of bc equal to f of c minus gamma bj, which is not equal to 0 because of our choice of gamma, that c minus gamma bj for j not equal to 1 is not a root of ai. That is, the roots of f of x are a1 to an. Definitely, other than a1 to an will not satisfy f of x. That's why we say that h of bj not equal to 0. Also, since x minus b the whole square will not divide g of x minus b square cannot divide the greatest common divisor of h of x and g of x. Thus, x minus b is the greatest common divisor of h of x and g of x over some extension of k. But then they have a non-trivial common divisor over k, which must be a divisor of x minus b. Since the degree of x minus b is 1, we see that the greatest common divisor of g of x and h of x in k of x is exactly x minus b. Therefore, x minus b belongs to k of x, where b belongs to k. Remembering that k equal to f of c, we get that B belongs to f of c. Since A equal to c minus gamma b, and since b comma c belongs to f of c, and gamma belongs to f, which is subset of f of c, we get that A also belongs to f of c. Therefore, in total we get that A, gamma, B are all in f of c. Therefore, A plus gamma B also belongs to f of c. This says that A belongs to f of c. Therefore, f of AB is a subset of f of c. From these two results, we get that f of AB equal to f of c. Thank you.